Okay, yeah, seems I'm not entirely sure how to use this. Yeah, yeah, okay, I get it now. But yeah, I'm going to be doing an overview of my BJX2 instruction set. It's basically my personal risk style hobby ISA. So yeah, so major features. It's a risk style instruction set. Kind of a lot of those exist, I guess, but well. So it uses variable length instructions that are either 16 or 32 bits or 16 or 32 or 48 bits. This depends on basically which profile is supported by an implementation. But my initial prototype cores are currently doing the more limited 16 and 32-bit instructions. It supports predicated instructions, kind of similar to those of ARM, but more limited in that rather than using full condition codes, they only use a true-false status. It also supports a wide execute feature, which I call WEX, but it can be compared or contrasted with both a pure scalar or VLIW style instruction set. Yeah, BJX2 is sort of a hybrid in that it is capable of operating in a scalar mode, but it also has some features analogous to those in a VLIW. But instruction encoding is quite different from something like a TMS 320 or an Itanium. But yeah. So uses 3264-bit GPRs, though a few of those aren't really usable as GPRs per se, so they're more special registers. That would include the stack pointer, and R0 and R1 are both used as special purpose scratch registers. It can operate in either a 32 or a 48-bit address space. This also depends on profile. The current Verilog implementation is doing a 32-bit address space. The MMU is optional, partly because TLB is kind of expensive. So for now I'm leaving it out. Future implementations probably will add a TLB. I have done previous prototypes with TLB. It's just not enabled in this case because, you know, cost. The design is little Indian and supports misaligned load and store as basically baseline features. Though, yeah, little Indian mostly because that's sort of de facto at this point. Pretty much anything with big Indian is kind of oddball and leads to more pain than it's worth. Misaligned is kind of similar because, you know, good old x86 and so on does it, and it doesn't really cost that much over the aligned only case. Does require alignment for some features, namely instruction load and stuff is required to be 16-bit aligned, but those are special cases. Also, the stack is required to be kept aligned, but that's also a special case. So, inspiration. Some instruction sets did inspire the design to some extent. Super H. Um, this is the closest to a direct ancestor. In particular, a lot of the core instruction naming and basic instructions are are fairly similar to those in the Super H4, which was the processor type used in the Dreamcast and also a few other things. But yeah, though there are quite significant differences at this point, and the instruction encoding is quite a bit different. It also takes some inspiration from ARM in that it has some similar features, but a lot of them are in a much more budget constrained form. Like, yeah, but I'm probably gonna get to that later. Also, it can be compared some to RISC-V, but this was more partly due to convergent evolution than an explicit design choice. Basically, through trial and error, trial and error and experimentation and so on, it generally led towards in a path that sort of started to, in some ways, become more like RISC-V than it was towards its original Super H ancestor. But yeah, and TMS 320 C6X and IA64 partly in yeah partly inspired the design or some aspects of the design of the explicit parallelism feature or WEX. Yeah, those designs, however, were using VLIW, whereas this design is not not exactly VLIW, but it is explicitly parallel. So in that sense, it has some commonality. But yeah, so it is a RISC in that it uses a load store architecture and it limits instruction complexity and latency. Yeah, in this in this case, RISC does not necessarily mean that it's aiming for a minimal instruction set size, nor is it necessarily aiming for like the simplest possible implementation either. Um, there are pros and cons of that, but yeah, but aiming for the simplest possible ISA wasn't really my design goal in this case. I was more aiming for like trying to gain like a reasonable performance on a reasonable implementation budget. What about ARM? Um, well, ARM has more complex addressing modes than BJX2. For example, it supports auto increment and or auto increment modes, and some modes like in some ways fancier than those even supported by x86. But yeah, in my case, I'm using a little bit simpler addressing modes, though still more than RISC-V. Um, ARM uses full condition code predication, whereas BGX2 only uses a true-false flag. Um, this does mean though that like this does mean though that like it uses less or fewer bits to encode the predication, so less encoding spaces is spent on this feature, but but yeah, it remains relatively useful. ARM also uses a shifter that's kept in line with the register and immediate fetch. This has pros and cons as well. Um, on ARM, this allows like shifts to be done in a good variety of instructions, but it costs indirectly, and it increases latency, which means that an ARM style core couldn't really be clocked quite as high, or at least not as easily. You could probably do it if you made the pipeline a lot longer or something, but yeah, in my case, I'm doing a 6-stage pipeline, which I didn't add a slide for, but yeah, might talk about that some anyways. But what about RISC-V? Well, RISC-V is simpler, in the simple case at least. Yeah, yeah. For example, RISC-V only supports load restore with a displacement, but doesn't support scaled index addressing, whereas BJX2 supports both. However, unlike x86, it's not possible to add or to both use scaled indexing and displacement at the same time, because those two features are mutually exclusive, and addressing modes available are more limited than those available in ARM. Multiplier. There is no quad word multiplier in BJX2. This again is partly for cost and latency reasons. I did try previously to implement a quad word multiplier in Verilog, but noted that I was dealing with designs that would both be relatively expensive and have a relatively high latency. Instead, it only has a double word multiplier and implements quad word multiply in software. This is reasonable, at least because quad word multiply is relatively uncommon, at least if compared with double word multiply. Hardware divide. BGX2 currently does not have any sort of hardware divider. Again, that's partly for cost reasons and partly for latency reasons. Contrast, like Super H had included an incremental divider. So basically, you could set up some registers and set up the initial state via div 0 instruction, and then use effectively chains of div 1 instructions to implement the divide. This was at least like relatively effective. However, I didn't do that in this case. It's one of those features that I may add later, but I've been sitting on it some. What about microcode or trap emulation? The downside of microcode is that it adds a lot of complexity in internal mechanisms, and it is simpler to not bother with having any complex instructions. So in the case of my current implementation, pretty much everything that the core that can be done in an instruction is done mostly via combinatorial logic and some state machines. Trap emulation is kind of an intermediate step. In this case, an invalid opcode would or you're an interrupt handler. That this hasn't really been done much in this case either, um, but could be done. Most, yeah. The downside of trap emulation, though, is it does have a relatively high cost, namely, namely due to the cost of interrupt handling. Code density, or variable length and code density. So, versus fixed 16-bit encodings. Mostly, mostly it's fixed length 16-bit encodings come at a performance penalty. Since like a lot of operations that could be expressed directly in a single 32-bit instruction would require multiple instructions to be expressed in 16-bit. This, in some cases, may actually come at a slight cost to code density as well, but primarily it affects performance due to requiring like anywhere from around 40 to 60% more instructions to accomplish similar logic if compared with something like a fixed length 32-bit encoding. This is not ideal from a performance perspective. Compared with fixed length 32-bit, fixed length 32-bit is reasonably good from a performance front. However, its main drawback is code density, and kind of the inverse ratio of the fixed length 16-bit case. Instead of needing more instructions, it uses fewer instructions, but it ends up needing around 40 to 60% more space. Space again is not entirely free, but if performance is the main concern, then the worse code density is generally an acceptable trade-off. Variable length, however, has the advantage of basically allowing the benefits of both cases, namely it allows a better code density of the 16-bit encodings, while also allowing for the better performance of the 32-bit encodings. The cost is, however, that it is slightly less simple, namely that potentially a good chunk of the instruction set ends up being duplicated by two different instruction decoders, and also there's a little bit of added complexity due to making the pipeline advance correctly in the face of variable length instructions, which is, while not too unreasonably complicated, is kind of a pain to get working. So, yeah. Is variable length not risk? In my opinion, not really. Because, risk by itself doesn't say anything about about necessarily having fixed length instructions. Though a lot of traditional implementations have used 16 or fixed length instructions. What about x86? Well, x86 is kind of the extreme opposite case. The main drawback of x86 is that it is not straightforward to determine the instruction length. Namely, since the instruction is determined by any number of prefixes followed by potentially multiple opcode bytes, and then followed by the whole like mod reg RM encoding at the end of it, which can in turn cover a whole range of links. This means this means that relatively complicated logic would be needed just to determine the length of an x86 instruction, much less actually decoding it. I'm yeah, I'm not actually entirely sure how conventional x86 implementations have managed to pull it off as well as they have, but they have apparently done so. Thumb2 and RISC-V compressed. Both of those are examples of variable length instruction sets. The original thumb was fixed length at 16-bit, but this in turn came at a penalty. Yeah. Namely, the original thumb came at a penalty both in terms of performance and its inability to directly access all of the registers via a good number of the instructions. Thumb 2 did sort of address this in that you can use 32-bit forms to access all of ARM's registers, but RVC is kind of simpler, but RVC actually went the other direction in that a much larger number of RISC-V compressed instructions can access all of the registers, but at the expense that there's a lot more limited range of instructions that can actually be expressed in terms of 16-bit forms. BJX2 is sort of a compromise between these two extremes. Yeah, namely in the BJX2, most of the two register instructions are limited to the first 16 registers, but the single register operations can generally access all 32. So one goal is to keep encoding simple. So ideally you want to make the length encoding quick and easy to determine. Namely, if you only have to look at a few of the high order bits to determine how long the instruction is and its general encoding blocks and other stuff like that, it makes dealing with the variable length encoding not nearly as much of a problem. So overall in encoding space, it's structured in terms of 16-bit words. So for the first word, when it looks at it, anything with the high order bits in the 0 to D range is all 16-bit land. 16-bit land is further divided from this, but in general, 0 to D. The whole E block is used for predicated instructions. Most of those are 32-bit. A 48-bit range also exists, but is but isn't used by this implementation or by the current Verilog implementation. The emulator does support 48-bit predicated ops as well, but these aren't really used much at this point. The F block is used for 32-bit instructions that are non-predicated. These ones are generally either scalar instructions or wide execute. Um, but both the E block and F block encodings are relatively symmetric with each other. So yeah, so so basically, an instruction in the F block will have a pretty much direct equivalent in the E block, and vice versa. Only the main difference being one is predicated and one is not. There are some instructions from the F block that are not allowed in the E block and vice versa, but for the most part the encodings are symmetric at least. um, so the FO to F3 blocks are used for scalar instructions or uh, execute if true in the predicated blocks. The F4 to F7 blocks are used for wide execute instructions or for execute if false in the predicated block. F8 and F9 are both used for for 16-bit immediate instructions, but are scalar slash true or wide slash false respectively. The FA to FB blocks, or yeah, FA and FB blocks are used solely for loading 24-bit immediates into DLR or RO, R0. Um, DLR is a name used for R0, which is effectively a special purpose register, which the use of this register is primarily for loading immediates and other things like that, namely ones that are too big to fit in the instruction coding correctly. To some extent, Super H also did something similar with making R0 special, but with the primary difference that Super H also tried to use that as a return value register and as a general scratch register, which led to a lot of like hassle and stuff. In my case, I've generally made both R0 and R1 effectively off limits to the CAVI and to general assembler code, which partly avoids this issue, though these registers can't, or those two registers can still be used with caution, although some things aren't allowed for them. For example, they can't be used as base registers for memory operations, and if doing so is used to trigger some special encodings, namely for PC relative and GBR relative addressing and similar. Oh yeah, and the FC to FF blocks, those are used for all the 48-bit encodings. I'm going to gloss over these for now, but 16-bit land. So the 0 block is basically the basic load and store instructions. Load and store instructions are pretty much about pretty much analogous in this case to the ones in Super H. The main difference is the main practical difference is the addition of quad word load and store, but yeah, and also there is a functional difference in that the RO or R0 forms are replaced by DLR forms, but otherwise equivalent in that sense, and also in that unlike Super H, RM is always used as the base register rather than which is the base register and which is the, the source or destination depending on the instruction. In this sense, it's a little bit more like ARM in the encoding sense. The one, yeah. Also, and it can be noted that the two registers are held in the low order bits in this case. This itself differs slightly from Super H. So the one block is used for simple two register ALU instructions. It also includes move and some other things, so that's mostly what's in this block. The two block is used partly for some instructions with a direct displacement, such as branch instructions and for immediate for instructions, or for 4-bit immediate instructions. In BJX2, all the branches only have an 8-bit displacement, but in my testing that does seem to be sufficient. I had experimented some with both 10 and 12-bit displacements, but hadn't seen much of an actual gain in code density due to having them. For any branches larger than this, it falls back to larger encodings. The entire 3 block is used mostly for single register ops. The 0 register ops are also included in this space as well. The use of an entire 12-bit block is a bit larger than in Super H, but it does allow for a wider range of 1R instructions. The encoding of the 1R space, so it does actually add an extra bit in here, so it does allow access to all 32 GPRs, unlike the only 4 bits available for the register in many of the other blocks. In the 2 and 6-bit blocks, some instructions are semi-redundant, but the main advantage here is that these 2 blocks effectively encode a 5-bit register via whether it's the 2 block or the 6 block. So the 2 block would encode R0 to R15, whereas the 6 block would encode R16 to R31. Some of the space that would have been used for the displacement or for the branch instructions in the R2 block is instead used for the GPR floating point instructions in the R6 block. The 4 block is used mostly for stack relative load store instructions, and also for the load effective or LEA instruction or load effective address. LEA, this exists partly because it is is useful for some things, though in the simple case it could be considered, or in the simple case it could almost be compared equivalent to adding between a register and R0 and then storing into another register, which there is already an add instruction for this in 16-bit land, but there are slight functional differences, mostly related to address space size and stuff. So the 5 block is more 2R blocks, or more 2R ops. Oh, nothing surprising there. 7 block is thus far unused. Interestingly enough, I hadn't run out of encoding space quite as quickly as I expected, so the 7 block is still available for now. The 6 block was used up only recently, but yeah. The 8 block is used for some load and store instructions with a fixed 3-bit displacement. This is 1 bit smaller than the 4 bits available in some of the Super H like load and store ops, but does work effectively. The SP rel like load and store ops do use a 4-bit displacement though. But no. The 9 block is used for the floating point unit, at least if using floating point registers. This is this is an optional floating point unit in the F-Pro or in the light profiles, and is not currently supported in the Verilog implementation. That it's instead using the GPR floating point instructions. Interestingly enough, I was able to fit a floating point unit that did both single and double, and so on, without using modes in a similar amount of encoding space to that used by Super H. So it's sufficient. The use of modes in Super H was one of the great annoyances with its FPU design. Also, the use of split registers made it like rather problematic to try to implement in Verilog and have anything past timing. So A and B blocks. These are effectively used for loading, well, when combined, a 13-bit immediate into DLR or R0. They're actually treated as two different 12-bit immediate loads, one 0 extending and one 1 extending, but yeah, but taken together they can be seen as a 13-bit immediate. For many uses, 13 bits is fairly useful. A C block is used for adding an 8-bit sign extended immediate to a register in the R0 to R15 range. Similarly, the D block is used as a load immediate instruction, which loads an 8-bit sign extended immediate into a similar range of registers. Via the 6 block here, there's also instructions to add and load a 4-bit immediate into R16 to R31, but while not particularly symmetric, it is useful at least. Though the code density advantage from this admittedly was relatively small. So 32-bit encodings. The F0 block contains mostly the 3 register and 2 register forms. So F3 registers have basically the two registers as before, and they also have the E and O registers. The O register. The E field basically functions or serves a role similar to that of the rec similar to that of the Rex byte in x86, but it's fixed. In this case, it supplies the third bit for the other registers. It also supports a Q bit, which is used among other things for selecting either between 32 and 64-bit operations, or in other cases between sign and zero extending. There are some sign and zero extended instructions. The F1 block is used solely for load and store ops at this point. Well, almost solely. Yeah, basically, this functions similarly with the two registers and the E field in the same spot. And here it uses a 9-bit displacement, or load store displacement. The D field here is 8 bits plus the bit that would have been used for the O register is used as the 9th displacement bit. The F2 block is basically an analogous encoding, except it's used for a 9-bit immediate instead. This is used for a lot of basic ALU ops that can use a 9-bit immediate. There's also some encodings that use a 10-bit immediate and a single register. This is used mostly for things like compare operations and similar. F3 block is currently reserved and unused. This block might be used for user extensions or something, or might be used in the future. That's partly up in the air still. The F4 to F7 blocks effectively mirror the F0 to F3 blocks. So the encodings are equivalent, the instructions are the same. The main difference is these ones would be differently predicated or wide execute rather than scalar. Yeah, F8 is, as noted, the instructions with a 16-bit immediate. In this case, the Z field encodes the 5th bit for the register, so it does function as a 5-bit register in this case. F9 effectively mirrors the F8 block, so similar to how these ones work. Yeah, the FA and FB blocks are similarly used to load what amounts to a 25-bit immediate into R0 or DLR. The 25-bit immediate case is useful in a lot of the cases where it doesn't fit into a 13-bit immediate, and similarly in cases where it doesn't fit into the direct immediate of one of these instructions. So yeah, though in a lot of these cases, it can either fall back to a 3-register form if needed, or what it can do is it can use some 16-bit pops back in the 5 range and stuff, which do, or some of which are basically effectively a three register op, just using RO as, or R0 as one of the fixed registers. So yeah. So predicated instructions. These all exist in the E block, with E0 through E3 encoding execute if true, and E4 to E7 being execute if false. These are controlled by the SR.T flag in the status register. It is a single bit in this case, as opposed to a condition code, or as opposed to a fault condition code. Similarly, the 16-bit instructions also have execute if true or execute if false. This basically means that you can conditionally load a constant into a register, or conditionally add something to a register or similar. Wide execute. Yeah, instructions can be marked as explicitly scalar or wide executed. Scalar instructions will always be the last instruction of a sequence of instructions in a wide execute sequence. So basically zero or more wide execute instructions can precede any scalar instruction. The scalar instruction effectively terminating the sequence of instructions that can be executed in parallel. Implicitly, these instructions are packed into lanes where the first lane is always the last instruction, and they effectively proceed in reversed order. So the scalar case is first lane only, other lanes are unused. This one would use 2 lanes, with the second lane coming before, and in the 3-lane case, the third lane would come first, followed by the second, followed by the first. Unlike something like a VLIW, you wouldn't need to fill this space with knobs, since all you have to do is leave it out in this case, within the limits of some encoding restrictions and similar. Profiles and minimal implementation support. Basically, several profiles were defined, which define which kinds of features the code or the code that was generated expects to be able to use in terms of wide execute. There is a provision for running code that expects to be able to do things that aren't actually supported on a core, which is that if it tries to do, or if it requests to do so via requesting a profile, and it doesn't support it, then it can effectively disable the WEX feature. This forces execution back into scalar mode. Any valid WEX sequence is also required to be able to behave as expected if executed in scalar order. This effectively allows a scalar implementation to run any WEX code as well. Yeah. The minimal implementation support required is basically just just to like just to ignore it and treat it as if it were scalar. In this case, in the case of a scalar implementation, for example, you, yeah, yeah, but in the case of a scalar implementation, the f the f0 to f3 blocks, or actually in this case the f4 to f7 blocks, would be treated more or less as exactly equivalent to their analogs in the f0 to f3 block range. Yeah, so yeah, it doesn't cost too much to support this feature or pretend to support it. Some other instructions related to this are required to effectively behave as NOPs in this case, but NOPs are cheap. Pros, cons versus superscalar. Well, superscalar does avoid the compiler needing to deal with some amount of these issues. As the idea is like in superscalar, the compiler can more or less just emit straightforward code and have the CPU do its magic depending on which magic it is capable of doing. The cost, however, of superscalar is that it requires a somewhat more complicated implementation, namely, in addition to just having the the additional execute units and the additional pipeline mechanics, one also has to deal with a bunch of additional complexity in terms of detecting which instructions depend on each other and other stuff like that. And in the first stages of decoding, you can't know for certain whether or not two instructions will be able to be executed in parallel, or whether they'll have to be split up and executed individually. This in turn adds complexity, making the encoding explicit and making it either be enabled or disabled does avoid some amount of this cost and allows potentially higher performance from a cheaper implementation. The, the analogy here would be more or less trying to fit a 2 byte implementation on a 50,000 50k look Spartan S7 or similar, like what you'd get in RDS 750. It's one of those cases that you can basically potentially fit a 2 wide implementation on that FPGA via something WEX like, but it's less likely that a good superscalar implementation would be able to be made to fit. Pros, cons versus VLIW. Well, the main advantage over VLIW is mostly code density, namely because scalar code and code with a limited amount of parallelism can still be expressed relatively efficiently, the code density at least doesn't go in the toilet. This was basically one big drawback of things like that, or things like the Titanium and similar, was when you effectively had 128-bit blocks with 3 instruction spaces in them, but more or less all of the instruction spaces need to be filled, then, well, that's not good for code density if you can't use all of them effectively. So in that case, a lot of the instructions would end up being NOPs, and code density would suffer, like, pretty bad. In this case, it's not quite as bad, since you can fall back to scalar, and if you don't care as much about performance, you can actually fall back to scalar and use the 16-bit encodings, which in the case of of a core that only did Wex and lacked superscalars, the use of 16-bit encodings would of course come at the penalty of only being able to run a single instruction at a time. That is basically, yeah, the end of this part. As can be seen, this is the actual instruction listings. So looking around, so the spaces which are slashes are ones which existed at one point but have since been dropped. For example, these were originally used for loads or stores with a 5-bit immediate, but these became redundant and have been dropped since some time. I've not had any other instructions that have really needed to use this space, so it's not been reassigned or anything yet. So the zero block, as noted, is each of the store instructions in byte word, double word, or quad word, with a similar naming convention to that used in Super H, but yeah, and a similar pattern as well, but with DLR instead of R0, and also the functional difference that DLR is scaled in this case, whereas R0 was unscaled in Super H, though this in turn is prone to depend on context. Namely, if PC or GBR is used as a base register, then DLR will be unscaled, and those encodings are based on using the RM field being 0 or 1. So nothing too unexpected here. So add, subtract, then add, carry, subtract with borrow, test, and or XOR. Then there's the move instructions. This encodes 4 instruction spaces, since effectively move has access to all 32 registers, and this is what happens when you want all 32 registers. Namely, it uses 4 instruction spots. So then, compare instructions. Nothing too unexpected here. The greater than or equal to compare is technically optional, since you can do almost exactly the same things with the greater than compare. The main difference, though, is that in the greater than compare, sometimes you need to be able to flip, or sometimes you need to be able to flip the immediates or flip the 2 arguments, and also invert things in order to encode the various conditional possibilities, which doesn't really work so well if an immediate value gets involved. In this case, you kind of need a greater than or equal comparison in order to actually compensate and allow all these possibilities in roughly the same way um, while dealing with immediates. The specifics get a little bit subtle in this case, but more or less that's how it works. You can get by just with a greater than compare if you always treat it like you're doing a comparison between two registers and ignore the possibility of, trying to make it behave like it had an immediate. So view cases also exist for dealing with an immediate. In this case, these are ones only compare the low 32 bits. So yeah, and you compare with a Q in it. That's for quad word, but anyone without a Q is for effectively double word. There are reasons for keeping those separate in this instruction set, but things like test and sim are sort of the same way. And we can also see see a zero extending stack relative loads here. So these also exist. Go. So the 3 block remains as the single register block. These fixed displacement shift instructions were previously treated entirely as special, but has since been repurposed reworked mostly to decode as if they were using the barrel shift instruction. But so these have been rerouted through the barrel shifter, but otherwise they're basically simple cases. While it might seem kind of redundant to have like operations that only shift by a fixed number of bits if one also has a barrel shift instruction, these are sometimes useful in various cases for actually saving some space. Otherwise, I probably would have dropped them already, but yeah. Yep. So nice collection of swap instructions. These ones, via like chaining the correct sequence of swap instructions, it's possible to achieve any combination of 4 or 8 element swaps, but the actual way of doing so is fairly convoluted, and in the 8 element case involves like a pretty absurdly large lookup table, so it's a trade-off there. Not much notable here. Some stack relative loads and stores, and with a 4-bit displacement. As noted, these exist for both both R0 through R16 or R15, and also R16 to R31. That's the difference between RN and RK, is the which group of registers it applies to. Also some for accessing control registers and shadow registers, but these no longer actually exist in instruction sets, so put them as question mark for now. Since these registers don't actually exist anymore, so question of if an instruction is still needed for them might matter if something were re-added. I don't know. These are control register cases are less commonly used since so you could probably get by with only a 32-bit encoding for these, but it's sufficient. So Leah does about what one would expect. Here's the registers with which use the R0 or TLR as the explicit middle operand. These cases are sometimes useful in dealing either with a lack of an instruction with a sufficiently large immediate, or in composing complex expressions. These can sometimes express these more compactly, or those cases more compactly, via not requiring is the use of as many move instructions, though the gains are relatively small. Yep. So here are the GFP operations, or GPR floating point. So effectively all you have is add, subtract, multiply, and some conversion to and from float, and also to compare offs, at least in terms of 16-bit encodings. This actually has relatively good coverage in terms of floating point support. Can be noted that, sort of like in the case of integer divide, there's no floating point divide in BJX2 either. Yes, it was existed previously, but was left out again mostly for cost reason, and partly because the cost of doing Newton-Raphson in software isn't too much higher than that of trying to do it via a state machine, so seemed reasonable enough to just leave out that instruction. Similar applies to square root. And there is the single to double instructions are quite heavily used in GFP, though, partly because the FPU instructions only work with double precision values, and there is no dedicated load or store instruction for single precision values. So the way those are accomplished is by loading a single precision value into a GPR and then just converting it over to double, or converting it back to single when you're ready to store it. half precision is supported in a similar way, albeit it, it's using 32-bit encodings in this case. And these instructions, as noted, partly mirror the first ones, and few instructions exist which exist solely to support R16 to R31. These can be used in some common cases like incrementing and decrementing and other stuff like that, or for loading small immediates, or at least loading those without needing to resort to a longer instruction. In the case of these double word loads, you can do some cases which have a 3-bit or effectively a 3-bit displacement. And the cases where the displacement is 0 have been partly repurposed for as a 0 extending load. The 9 block is, as noted, only existing if you have an FPU that uses floating point registers, which is not the current Verilog implementation. Again, this goes back to cost as well. Namely, it turns out to be cheaper to not have floating point registers than to have floating point registers. In terms of like performance or code density, the use of GPRs has resulted in slightly worse code density, but not too much of an impact on performance. So more or less we covered these already. And the overall block layout, yeah, it's been noted already. So this part's about the same. And we have good old 3 register operations. It is possible to actually use a fixed length or fixed length subset using only 32-bit encodings, but yeah, that has the usual drawbacks of fixed length 32-bit encodings. Namely, it comes at a code density penalty. However, as can be noted, predicated instructions and WEX are currently only available via 32-bit encodings. So yeah, no 16-bit for those. But those cases don't matter as much in that sense. Similarly, you can prioritize whether you want 16-bit encodings and better code density, or using 32-bit encodings and WEX for better performance based on a compiler flag for whether to optimize for code density or performance or similar. With the current default being, to try to make a balance. So it's, yeah. And yeah, there is a quad work multiplier defined in the encoding, but it's basically as an extension and not supported by the current implementations. So, same. So this is similar to the 1 block and 1Z block in 16-bit land. So, except main difference is less move. And you also have the control register moves here as well. Oh yeah. GSV is basically simmed instructions. So yeah, BJX2 does include basic SIMD instructions, but these are optional and stuff. So, impact, convert, and similar. Yeah, add S and add U. There's explicit instructions for sign and zero extended adds. These ones differ from the normal quad word operations, mostly in that they sign or zero extend the result up to 64 bits. This is also sometimes useful, such as like when dealing with integer operations, which in turn need to, for whatever reason, be converted up to long or similar. Also, partly because my compiler was kind of crappy and was sometimes resulting in cases where what should be integer values were exhibiting different behaviors depending on the contents of the high order bits. So or explicit sign or zero extending operations does, lessen that particular issue, at least in the sense of not having to go and find the other bugs, but yeah. The 9 block is similar in that it assumes the use of floating point registers, so not used in this case. And there's 20-bit or branches with 20-bit displacements as well. If one block is noted is mostly load stores, and similarly in regards to the whole floating point register issue thing. There's also conditional compare and jump instructions as another extension. I've not included them in the current implementation, mostly because of cost and latency. Performing both a compare and a jump in a single instruction actually does turn out to be not optimal from a cost or latency perspective. Effectively, you could split it up into multiple cycles and do it that way to deal with the latency issue, but by that point you may as well just have separate compare and branch instructions. So it is how it is. Nothing too unexpected here. Add multiply, add a sign or zero extension, and or XOR. You don't need a separate subtract instruction, since adding a zero extended value or adding one extended value accomplishes the same basic purpose. There are, of course, the usefulness of instructions with um, uh, shift with by immediate instruction. This does about as much as one might expect. Though the shifter does function in a way similar to that of the Super 8 shifter, in that positive shift values shift left and negative shift values shift right. This avoids the need for separate shift left and shift right instructions. In both these cases, the shift amount is treated as modular to the size of the value. So, yeah. So, yeah. The single register with immediate instructions are mostly used for test and compare. There was some constant loading ones available, but these have been dropped since these became effectively unnecessary once the F8/F9 block became available to Wax. So, but that wasn't the case originally. And so it's slash since they're dropped, but they haven't actually been fully removed yet. Well, F8 block is straightforward enough. So half of it's used for loading an immediate, the other part for adding or load with shift. Yeah, the load with shift instruction is basically the main way constant or larger constants are handled in this instruction set, namely that you can load the high order bits first and then have an instruction which shifts those bits left and tacks on another 16 bits or so, and you can repeat this however many times as needed until you get the full width constant loaded. This does work out potentially cheaper in many cases than trying to load, and then trying to do a load from memory, as would be more traditional solution. But the cost of loading from memory is that it is both kind of slow and kind of a major pain. If there's one thing that kind of really screws with branch length optimization, it's like randomly dumping like big blobs of constant values at semi-arbitrary locations within the section of code being emitted. In this case, you'd dump the blob of constants down and you'd surround it with a jump or similar so that it's jumped over. But yeah, both ARM and Super H kind of did it that way, and that kind of sucked. So, but yeah, I did it this way because this sucks slightly less in my opinion. So yeah. And obvious enough, except slight editorial change there. Yeah. And the 48-bit instructions exist, but I'm going to ignore them. And I've already talked about Wax. Yeah. I will consider this I consider that I've probably gone over what I'm going to go over right now, so this will be all.